Everyone, in this video lecture, we would be looking into some important chemical reactions of phenols, right? And as the heading says, electrophilic substitution reactions. So we already know about the basic of electrophilic substitution reactions, right? We know that electrophile, what is an electrophile? Electrophile is a positive reagent, right? And it will always attack the organic compound at sites of high electron density, right? At negative sites, right? So here we have an electrophile, which is a positive reagent, right? And it will always attack organic compound at negative site, right? And we know that these negative sites are sites of high electron density, right? So in this case, our organic compound is phenol, right? This is our organic compound. So we need to look into the sites of high electron density, right? Because as I said, this is an electrophilic substitution reaction. That means electrophile would be attacking this phenol molecule at regions of high electron density, that is at negative sites. So let's first see where are these negative sites, right? And to know negative sites, we need to look into the various resonance forms of your benzene nucleus. So let's quickly see the regions of high electron density. We know that this is your oxygen, and the oxygen has two lone pair of electrons, right? And one of the lone pair of electrons of this OH bond, right, will enter into resonance, or we say that it enters into the benzene nucleus, right? Or what the term that we use is that the lone pair of electron will enter into resonance, right, with the benzene nucleus, right? So this is what we are looking into. So we'll be looking into those regions of phenol where this lone pair of electron would be creating negative sites, right, or sites of high electron density, right? So here you have oxygen. Now, since the lone pair has moved into benzene nucleus, we have a double bond here, right? And we have a positive charge at oxygen atom, like this, right? So this electron pair has moved at this position, right? And we know that this position is an ortho position. This electron pair has moved here, and this is an ortho position. This will remain, and this will remain. Now, this will again move, since this lone pair will move into the benzene nucleus. Now, this will also move, right, like this, to this position, right? And this position we know is a para position. This is positive. Like this, right? It will move here. Right? Now, this is also the second region of high electron density. This is the first region, this is the second region. Now, this will again move. Right? This will also move. And we'll get to know about the third region of high electron density of phenol molecule. Right? So when it will move here, at this point, we have a region of high electron density. So now here, this is negative. Right? So these are the various resonance forms. And you can now, from these resonance forms, you can see very easily. From here, you can see that first, this lone pair of electron has reached this ortho position, right? This is your ortho position. Then it moved to the para position, right? This is your para position. Then it further moved to the second ortho position, right? So we have, in short, what we will write is we have regions of high electron density. We have regions of high electron density at ortho and para, right? That means how basically these ortho and para, how basically these negative regions are created, right? This is done with the help of this OH group, right? So basically this OH group is creating regions of high electron density at ortho and para positions of benzene nucleus, right? So we will say that your OH group, right? Your OH group is ortho and para directing, right? When we say ortho and para directing, this means that it will direct or it will introduce the electrophile at ortho and para positions. Direct or introduce the incoming electrophile at ortho and para positions, right? So when we will be looking into the various electrophilic substitution reactions of benzene ring, right, the electrophiles that we would be looking into is like maybe like bromonium ion. This is an electrophile. Like nitronium ion. This is an electrophile. Sulphonium ion. This is also an electrophile, right? Methyl group, right? Or your acyl group, COR, right? All these are electrophiles. So when electrophilic substitution reactions are done on benzene nucleus, the incoming electrophile, these incoming electrophiles will move at or will go at ortho and para positions of benzene nucleus, right? So basically, if this is your phenol, right? So these are ortho and para positions, right? Where these electrophiles will enter, right? So basically, what we would be getting is an ortho and a para product, right? While doing the electrophilic substitution reactions of phenol molecule, right? So now let's quickly look into, and one very quick thing, since we are looking into the various resonance forms of phenol molecule. If you look at this, when this lone pair of electron has moved into the benzene nucleus, we have a positive charge on this oxygen molecule, right? This is your positive charge. This is your positive charge, right? Now, due to this positive charge, right, we have a bond pair of electron between oxygen and hydrogen. Due to this positive charge, the bond pair of electron would be attracted towards oxygen atom because it has a positive charge, and we know that bond pair is always a bond pair. It's an electron pair, so it's a negative, right? It has a negative charge, right? So this bond pair of electron will move more towards oxygen atom, and that will ease, or due to which the hydrogen atom will easily leave the phenol molecule, right? Or it will easily ionize, right, to release this hydrogen ion. So in phenol molecule, this OH bond will ionize, right, like this, in this space here, right? It will ionize to give you this phenoxide ion plus your hydrogen ion, right? And since due to this lone pair of electron which entered into the benzene nucleus, the oxygen atom has acquired a positive charge, right? And due to which the release of hydrogen ion has become easier, right? The hydrogen ion would easily be able to move, or it will easily, the hydrogen ion will easily ionize and enter into the solution, right? So whenever we have hydrogen ions, we know that the compound is acidic, right? So this tells us that why phenol molecule is acidic, right? So let's quickly move, and now we'll look into some of the electrophilic substitution reactions of benzene nucleus, right? The first reaction that we would be looking into is, so now we know that your OH group, hydroxyl group, is an activating group, or basically we say that it activates your benzene nucleus. It will activate the benzene nucleus. This is your benzene nucleus. It activates the benzene ring at your ortho and para positions, right? This is important. Now let's look at the first reaction, which is your halogenation, right? Halogenation. In halogenation, what we will do is, when phenol molecule, right, when phenol is treated with bromine water, right, it will form, the product that we will get is a polyhalogen derivative. This, we get a polyhalogen derivative, which is 2,4,6 tribromophenol, right? So in 2,4,6 tribromophenol, both ortho and para positions would be occupied by your bromine electrophile, like this, right? This is your 2,4,6 tribromophenol, right? Now we have done this reaction with excess of bromine water, right? This reaction is done with excess of bromine water, right? And if the same reaction, right, if the phenol, if instead of water, right, we take some non-polar solvent like carbon disulfide or carbon tetrachloride, then we will not be getting this 2,4,6 tribromophenol. Instead, we will get ortho and para product separately. Let's look at that also. We have bromine, right? This time in a non-polar solvent. Here we had a polar solvent, which is water, right? CCl4 or CS2, right? When your solvent is non-polar, the product that you will get is your 2-bromophenol, right? Or orthobromophenol. This is your orthobromophenol. And this is your para-bromophenol. Now, what is the reason that when we used bromine water, we got 2,4,6 tribromophenol, but on using this non-polar solvent, carbon disulfide or CCl4, what we got is your ortho and para product separately. The reason is that in polar solvent, water, right, which is water, your phenol molecule, right, your phenol will ionize, right, to give you this phenoxide ion, right? It will give you this phenoxide ion, which is much more reactive as compared to phenol, right? So this phenoxide molecule, this phenoxide ion will activate this benzene ring more, right, compared to phenol. Because here, in this case, since we have this non-polar solvent would not be able to ionize. Non-polar solvent, in non-polar solvent, no ionization of phenol molecule, no ionization of phenol molecule. And so no ionization of phenol molecule means it exists as phenol, right? In the previous video, like in the previous slide, just when I started the lecture, I said that phenol has ortho and para directing sites, right? But if we look at phenoxide is more stable than phenol, right? We have discussed this in a different video lecture. So this phenoxide will activate the benzene ring to a larger extent compared to phenol, right? Since your phenoxide ion will activate the benzene nucleus to a larger extent, so we get 2,4,6 tribromophenol. Whereas in this case, since there is no ionization of phenol to form phenoxide ion, it is less activated, and what we will get is your ortho and para isomers, right? I hope this is clear. And the other thing that we need to look into is that out of this ortho and para, this is your minor product. Ortho product would mostly be the minor product, and this is your major product, right? Why this is minor product? Because if you look at this molecule, it has more crowding, because this bromine atom is near this hydroxyl atom, right? The hydroxyl group, I'm sorry. Since bromine is near to hydroxyl, so we have more crowding in case of orthoisomer, right? We have more crowding, due to which this is less stable, right? This is less stable. So this would be in minor quantity. Whereas if we look at this Br, right? This Br is far from hydroxyl group. This group, this Br is far from your OH group, right? So we have less crowding, or what we say it as steric hindrance, right? You should be familiar with the term steric hindrance, right? So we have less steric hindrance, right? Or what we say it as crowding, right? Due to which this isomer, your para isomer, would be more stable, right? So this would be in major quantity, right? We would be looking into this, into the similar thing where ortho isomer would be in the minor quantity and your para isomer would be in the major quantity, right? The reason would always be the same, right? Now let's quickly look into the other reaction, which is your nitration, right? Nitration of phenol. Nitration of phenol. So the OH group present in phenol, right? This is your OH group. OH group present in phenol activates the ring, right? To such an extent that some phenol can be nitrated even with dilute nitric acid, right? If you take dilute nitric acid, right, at low temperature 293 Kelvin, you will get ortho and para product, right? Here the electrophile is this NO2 nitronium, and it will always attack ortho and para positions. Why? Because OH group activates your ortho and para positions. Just remember this concept while looking into these reactions, right? So this is your orthonitrophenol, right? You will get para-nitrophenol, right? I hope this is clear, right? So we also call it as, if you look at the position, this is 4-nitrophenol, this is 2-nitrophenol, right? Now this is with dilute nitric acid. Now let's do this reaction with concentrated nitric acid. If we treat phenol with, say, concentrated nitric acid, what we will get is the similar product that we get while doing halogenation, 2,4,6 trinitrophenol. Right? You have NO2 here, you have NO2 here, and you have NO2 here. Right? Plus 3H2O. We call this, the name of this product is, IUPAC name is 2,4,6 trinitrophenol, right? Or we call it as picric acid, right? We call it as picric acid. This is important reaction, right? Picric acid we get when we use concentrated nitric acid, right? With dilute nitric acid, we get orthonitrophenol and paranitrophenol, right? And remember that orthonitrophenol would be in minor quantity and paranitrophenol is in major quantity, based on the explanation that we have seen in the previous reaction, right? So here we need to consider one thing, that the picric acid that we got, right, by direct nitration, the picric acid that we got is in low quantity, low yield, poor yield, or what we say is poor yield, or we got this picric acid in less quantity on doing direct nitration of phenol, right? So what we generally do is, in order to get large quantity, right, or in order to get picric acid in good quantity and good yield, what we do is we adopt some indirect methods, right? In indirect methods, what we do is we first do sulphonation of phenol, right? Like this. Let's see it over here. This is your phenol molecule, right? What we will be doing is we will take concentrated sulfuric acid, right, at 373 Kelvin. We will get ortho and para benzene, sorry, ortho and para phenol sulfonic acid, SO3H, right? The other is your para product, SO3H, right? This is your paraphenol sulfonic acid, and this is your orthophenol sulfonic acid. Now what we would be doing is, we will, since this is an indirect method, we got first this ortho and para or phenol sulfonic acid, I'm sorry. Now we will heat it with concentrated nitric acid. On heating with concentrated nitric acid, we get picric acid in good yield. Right, we get, sorry. So this is the method using which we can get a good yield of picric acid using indirect method. And in this indirect method, what we did, we first carried out sulfonation of phenol, right, to get ortho and para phenol sulfonic acid, which then we heated with concentrated nitric acid to get 2,4,6 trinitrophenol, right, which we call as picric acid. I hope this is clear. The simple thing is, phenol, even with dilute nitric acid, gives you ortho and para product, right? If you heat it with concentrated nitric acid, this is your direct nitration. You get 2,4,6 trinitrophenol, which is your picric acid, but we get picric acid in low quantity by doing direct nitration. So what we do is we adopt an indirect method where we first heat the phenol molecule with your concentrated sulfuric acid at 373 Kelvin, and it gives us your it gives us your ortho and para phenol sulfonic acid, which on heating with concentrated nitric acid will give you 2,4,6 trinitrophenol, or we call it as picric acid. Right? I hope this is clear. Now let's quickly look at the other reaction, which is your sulphonation. Right? We have already done this in indirect. We have just done this in indirect preparation of picric acid. Sulphonation. When we say sulphonation, we are introducing a sulfonic group, right? SO3H group, right, into your benzene nucleus, right, into your benzene nucleus, right? And this sulfonic group, this is your electrophile, right? Just know these things. This is an electrophile, which is a positive reagent, right? And it attacks the phenol molecule at regions of high electron density, that is at negative sites, right? Because it is positive, so positive always attack at negative sites. So we will take phenol, again the similar reaction. We take phenol, right? We heat it at low temperature, say at 293 kelvins. When you heat it with concentrated sulfuric acid, you will get ortho product. At low temperature, you will get ortho product at low temperature, which is your major product in major quantity. Right? Now, if you do the same reaction at 373 kelvins with concentrated sulfuric acid, what you will get is para product, SO3H. This is your sulfonic group, which is an electrophile. Now it is attacking at the other negative region, or the other negative site, which is your parasite. This was ortho and this is para. Right? I hope this is clear. So this would be the major product at 373 kelvins. Right? And if you here in this reaction only, if you raise the temperature, right, to 373 Kelvin, you will get para product. Right? So ortho isomer can be changed. Basically, this is an ortho isomer. This ortho isomer can be changed anytime to para isomer by raising the temperature or by heating. Right? I hope this is clear. Just remember which is the electrophile. Electrophile is SO3H. Right? Since this is an electrophilic substitution reaction of phenol molecule, right? And we know that phenol, this OH group is ortho and para directed. So the product that you will get have electrophile at ortho and para sites, right? Just remember this. Now we'll be looking into very important reaction, which is your Friedal-Crafts reaction, right? You have done this in other chapters also, right? Friedal-Crafts reaction. In Friedal-Crafts reaction, firstly, this is a way to introduce, using Friedal-Crafts reaction, we introduce your methyl group or your acyl group. Acyl group is your COR, right? Methyl group or acyl group into the benzene nucleus, right? Into the benzene nucleus, right? So let's quickly look at the reaction. Since this is an electrophilic substitution reaction, so this R or COR are electrophiles. These are electrophiles and would be introduced at the negative regions of phenol, that is ortho and para regions. Right? So what we basically do is, in Friedal-Crafts reaction, we make this phenol molecule, this is your phenol, to react with methyl chloride, right, in presence of aluminium chloride, right? It will form ortho and para products. We will get here CH3 plus OH, CH3, right? The name is, if you remember, this is your orthocresol, right? And this is your paracresol, right? And IUPAC name is, this is one, right? This is one this is one, this is two. So this is 1-hydroxy 2-methyl benzene, right? This is 1-hydroxy 4-methyl benzene. This is fourth position. So 1-hydroxy 4-methyl benzene, right? And which one of these would be in the major quantity? This would be in the major quantity, and this ortho isomer would be in the minor quantity. What is the reason? We have studied before. We have gone through the reason before when we started it. This has more steric hindrance. More steric hindrance. And why more steric hindrance? Because these groups are near to each other, due to which there is more crowding, right? And this is little unstable compared to para-isomer, in which methyl group is far from OH, right? So there is less crowding, less steric hindrance, which means this is more stable. So this is in major quantity because it is more stable. Right, now let's look at the other reaction where we will introduce this COR group into the benzene nucleus. Right, and one important thing is that the yield is poor, right? The para derivative, as it predominates, but the yield is poor in this case. Why? Because this aluminium chloride, right, that we have used in the reaction will react or coordinate with the oxygen, right? It will coordinate with the oxygen atom of the phenol molecule, right? So this phenol will start reacting with this aluminium chloride, right? Due to which we have low yield of ortho and para products, which are the main products of this reaction, right? The only reason is that this aluminium will coordinate with the oxygen atom. If you remember, aluminium, right, this is an exception to the octet rule, right? And it has 6 electrons in the outermost shell, right? And we know that oxygen has here 2 lone pair of electrons, which it can donate to the aluminium. So aluminium, basically this is a coordinate bond, right? Where this aluminium chloride coordinates with the oxygen atom. It takes the 2 lone pair of electrons and form bond with it, right? So basically phenol is undergoing a secondary reaction, right, due to which there is poor yield of main products, right? Just understand this, why poor yield. I hope this is clear. All these reactions are clear. In the next video lecture, we will look into some important reactions of phenol, right, which would be the Riemer-Tiemann reaction, Kolbe's reaction, right, coupling reactions. So just keep watching, right? And I hope everything is clear. Thanks.